from the quantum recording in progress. Okay, let's start. Okay.
Yeah, sorry, give me a second. Okay. Today we will I finally introduce these stabilizer states. But before doing that, maybe it's useful to do a recap of what we did last time. Well, I will not recap everything, just the things that I need, and then later on, if something useful pop-ups, then I just tell you again about that. So we discussed about the Heisenberg group in prime or dimension, which is the group with the following composition rule. So we have just the addition on the first factor, and on the second factor we have the appearance of the symplectic form. Then we saw that the center of this group.
Mirko?
Yeah.
Sorry, we had echo. We don't see your writing, I think.
Oh.
Maybe other people do, but like on two laptops, we don't see it here.
No, actually, I cannot see my writing on my phone too. So
yeah. So let's maybe.
Yeah. No, yeah, because I did the wrong sharing. Sorry. Okay. Now it's
okay.
correct.
H of P and the composition like you defined last time. Okay. We can continue. Thanks.
Okay. No problem. So yeah, we have this composition rule, and we saw that the center of this group is just isomorphic to the base field. And about this group, we also saw the form of the center fixing automorphisms, and we proved, well, or at least sketched, that these automorphisms are of the form of maps that send a pair VT into V T plus alpha of V. Sorry, it's not V, it's G of V. Where this G, well, for the Heisenberg group must be a symplectic matrix, and alpha is just a linear function. So we saw that these automorphisms form another group that is the affine symplectic group, and this is basically the semi-direct product group of the symplectic group with the phase space. So then we discussed about the representations of the Heisenberg group, and to do that, we introduce. So let's say presentation. We introduce a function from the center of the group into the unit circle, which is group theory called the character, and this is a function mapping an element T in FP to omega T to T, where omega is a root of the unity. So it's just this. And if we introduce a polarization of the group, so we just write the of the phase space as a Z component plus an X component, then we can define the operators W that can associated to such character. And these operators, when acting on functions, are defined as in the following way. As z u and for u plus x. And we argue that these operators are reducible representations of the Heisenberg group. Then we saw that they are traceless. I mentioned that they are traceless, and actually this is very easy to see. And that's because as matrices, up to the phase given by the character, these are just Z time X operators. And this the Z operators is an operator where on the diagonal we have all the roots of the unity. So the trace of this operator is 0, except when the label small z is 0, while x is of this form, basically something like this. So it's just traceless by default. So the only only the identity is a non-traceless operator, of course. And then we saw that by Stone fundamental theorem, these E-reps are basically classified in terms of this character. And so if we have two representations that agree on the center of the group, then they must be unitarily equivalent. And this is interesting for us because when we consider an automorphism, that a center fixing automorphism of the group, for example, a symplectic matrix. So if we have G in the symplectic group, then we have that the map W composed with G is unitarily equivalent to the original W, and then there exists an operator mu such that we have basically mu of G, W of B, mu of G dagger. This is equals to W composed G of B, and this is also equals to W of GB. So let's say it's like when we act on the symplectic on the discrete phase space here, and then we apply the representation, then we get this action on an operator level. I just want to finish the discussion about these operators, and then we switch to the qubit case. The first thing that I want to say is that we can obtain projective representations of the discrete phase space, and namely, we just need to find the operator W of Z X, which is just W of Z X 0. And this is one can see that this is a projective representation. Actually, it's coming from the general theory, but we can also, in principle, we can also do the direct calculation, for example, and this could be nice to check. You have that W is equals to I of T to the minus 1 BW W of B plus W. This is like the this is saying that these representations are projective because we have this non-trivial phase. And another thing that one can check is that these operators basically satisfy the canonical commutation relations, but in the exponentiated form. So we have that W of W. This does not commute because we have a non-trivial phase. But yeah, this is like in the bosonic setting. Oops, sorry. So we have W of W, WP. And yeah, honestly, I don't want to do this calculation now, but this is something that you can easily check. When you just need to, for example, act on a function and use this, where is it? This action here. And yeah, just check these two relations. Okay, and one last thing. Okay, now maybe at this point we can switch to the case, and I'll be rather sketchy because things are very similar at this point, but we need to take care of a couple of things in this case. The main problem actually in the qubit case is in the very definition of the Heisenberg group here, because with this composition law here we are using this 2 to the -1, and actually the multiplicative inverse of 2 for finite fields exists only when you are working with odd dimensions. So yeah, we need to modify this this symplectic term in this case, and actually there are I think a couple of ways to do that, but I just catch the the most easy one, I think. But another consideration is that if we stay still in the case of P opt, in principle, one can also define the while operator as just Z and X without the additional phase. And this representation is equivalent to the one given before, namely the one with the character here, right? But the problem, and in principle, we can do this also for qubits, but in this case, the problem is that we cannot reconstruct all the basically Pauli operators, because this representation, when restricted to p equals 2, gives us only the real part of the Heisenberg group. And yeah, you can just see that because these Z operators, of course, is this one, and the X operator is just this one, but you have no way to recover the Y operator because in this description there is no I. So we have to find another way to recover all the Pauli operators, and to do this, the idea is we start with the discrete phase space, but this time instead of multiplying by f2, we use z4. So this is the integer modulo 4. And we, so for hn of 2, we introduce the following multiplication rule. and the first factor is the same, but in the second factor we introduce a function that what Marcus called beta in his thesis, and I'm just following his notation. And this function must satisfy a couple of properties. Now I just give you the way it is defined. First, to define beta, you define gamma. It is a Z4 function on the first base. And this is kind of simple because given the polarization Vz you have that gamma of V is defined by Vz times Vx, but this time modulo 4, of course. And given this function, we define beta in this way. So we have gamma of V plus W minus gamma of V minus gamma of W. And then there is another term to 2Bz times W of X. Yeah, and so this is the function that we use in the definition of the qubit Heisenberg group. Let's put it this way. And by construction, then you have the following properties that, given this definition, are all you can all check easily. First, we have that beta of VV is equals to beta of 0V or beta of 0, and this is 0. And the second one is that this beta is a lift of the symplectic form in a couple of senses. The first one, if you want, is that beta of VW modulo 2 is just the symplectic form. And this is, of course, living in F2 now. And you also have this property. So beta of VW minus beta of WV, this is equals to 2VW. Yeah. Yeah, you can just check everything by definition. When you check these two relations here, maybe it could be useful to remember that in this case, the minus operation is equals to the sum, because this is just a property of fields of characteristic G. So it's like when you write the symplectic form in F2, you have just that this is the sum, but now you have V, I, W, M plus I, and you can just use the plus. That's what I mean. Okay. So now basically one would do the same as we did for the Heisenberg group in not characteristic. So now we will look at the center of this group, and yeah, you can do exactly the same calculation as in their case with the new composition rule, and you can check that this is just isomorphic to Z4. But the main difference comes at this point when you study the center fixing automorphisms. Now they are still of the same form, so you still have this property here, because actually this one is kind of general for all the groups constructed in the way as the Heisenberg group is constructed. So yeah, where this alpha tilde now is just a function on the phase space in Z4. But now we have the main difference, because as in the I didn't write that, but when you have this condition here, you obtain the compatibility condition for the beta function, and yeah, basically you obtain this relation here. So you have on this side this thing, and this is equals to this alpha tilde v plus w minus alpha tilde v minus alpha tilde w. And now we can in principle do the same as we did for in the odd case. So we recognize that these terms on the right is symmetric. So also the term on the left must be symmetric. And so you obtain the relation that 0 is just beta of GP GW minus beta of GW GP, and then you have minus beta of VW plus beta of WB. And yeah, using the properties of beta, this is just 2, and then yeah, 2 that multiplies GP GW minus VW. And we are using, where is it? This relation here. And so yeah, this is telling us that G is a symplectic matrix on F2. But now the problem is this left-handed side of this equation here does not vanish for any G. Yeah, so the thing is we cannot separate the two the G and the alpha function as we did in the odd case. And yeah, so basically that means that this function alpha actually just depends on G2. And the consequence of this is that the center fixing automorphism group does not have the nice structure as in the case of odd characteristic. We basically cannot say anything more about this. The only thing that okay, but no, I just tell you later, because actually this function alpha function is not unique, but you can at least fix that on a basis. And this is what you usually when you do calculation. Yeah, the main difference actually is that for in the odd case you can just make alpha equals to 0, for example. You're fine. But yeah, this is what we are using. But then yeah, this is the structure of the automorphism, and then you can go to representations again. And yeah, actually they are very similar, but there is only this prescription about the basically the center. So now because now you introduce the character on Z4. So this is just map from Z4 to the unit circle. And yeah, it's like mapping T to I to T. Sorry if you heard some noise. But that, yeah, this could still be useful to consider the character for the base field. Yeah, it's defined as before. And so this is just minus mapping T to -1 to T. And yeah, you just define the while operators after doing the same polarization thing as basically the character for Z4, and this is T minus Z times X, and then you have the Z operator and the X operator. And from this you obtain again the E-reps for the discrete phase space, just forgetting about the center, basically. And we can call this while operators. And as you, yeah, you may check with this definition here, if you just go in the case of n equals to 1, you just recover all the Pauli operators. So the identity and X, Z, and Y. Yeah. Now, yeah, and actually, even for this case, you have the similar relations for while operators. First, they are projective representation in the sense, yeah, as in the case before. So here you have the character on Z4, and here you have the beta. And so let's say these are properties. And the other properties that you have the canonical commutation relations again. But when you write canonical commutation relations, you don't have the character on Z4, but you have, yeah, the character on the base field, and you have the symplectic form in this case. Yeah, it's nothing too fancy. It's just that when you do the calculation with this relation here, is different things are popping out depending on properties of beta and stuff like that. Okay, and yeah, and then you can here you have this Stone Fundamental theorem. So two E-reps agree on the center. Yeah, it's the same story. So given G in the symplectic group, but now we also have this function alpha. Yeah, I just call this alpha with a tilde in Z4. Now you have that there exists an operator that depends on G and alpha, such that W of G V, yeah, it's just unitary equivalent to WP. Yeah, it's like you have these additional phases here, and in principle, I can also write you the explicit form that is, for example, very useful when you do classical simulation. This would be something like -1 to yeah, it's like sorry, if you want to write things explicitly instead of this alpha, yeah, you have this alpha, but you can choose alpha to be, I don't know, the form of this form here. So it would be a function on F2, yeah, in F2. Let's say we chose like this. So this is in Z4. I'm hiding some details that are kind of useless. And when you do this choice, you have that W of GB. This will be -1 to VU, and then there is these two. Sorry, no, sorry. You have this one here, this symplectic part that is coming from the fact that in the center fixing automorphism group, you also have the Heisenberg group, of course, or the phase space. And then you have the alpha part. So you have this additional function acting on V. And then, yeah, you have W. Sorry, I'm mixing up things. I'm really sorry. So here is like you have, okay. I should not improvise, I think. But yeah, that's the way you write explicitly these relations, if you want. You can read this as, yeah, it's like when you write U, P, U dagger for, let's say, in the standard formalism for Paulis. But when you want to rewrite this relation for in the symplectic language, then you will have something like this. Yeah.
I think this is nice what you say, but right now we have two equations that are the same kind of, right? So we have because I think you're saying that this alpha is like a phase factor, but
yeah,
maybe you need to have some u tilde or something like this that depends only on G. Can it be?
No, I think the right thing here is like this one, right? Is yeah, because it's like, yeah, this is like the Clifford as you would usually write when
that's
you
the Clifford element, and then it factorizes into the phase and the symplectic rotation.
Yeah.
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 Okay. Yeah. Then it makes sense. It's just that the equations were kind of the same, making the phase.
Yeah. Sure. I was mixing things up because, yeah, it's like, as I said before, I was more precise with my words. That my writing is like, if you want to write everything in a symplectic language, then you should ask, yeah, how do we write the action of Clifford, which of course acts by conjugation in this way, and the answer is given by this second term.
Yeah, and so basically for any Clifford, we get very many possible actions, or so I'm wondering because you said that alpha is just a function from the base field, from the phase space, right? So can I just choose it to be 0, and then I have already a construction, or I need to always.
You cannot always. The problem is that you cannot always choose alpha to be 0.
No.
Yeah, if you stay in this very concrete case here, you just choose alpha. You fix the value of alpha on a base. So, for example, you can choose alpha of EI to be 0. This is allowed, but that does not mean that alpha is 0 on every vector, basically, because actually this function is not linear. So
The statement is for any Clifford it looks like this, but for a Clifford I need to first compute them, yeah. So
actually you have to compute this function, and this is the most expensive.
But then it's the same as G. I mean, G I also have to compute what it is, so similar to Okay.
Well, yes, but if you want, the problem is that this of this alpha is more expensive. Basically, I
Mm.
think yes, yeah. Well, actually, it's cubic in and the computational alpha.
Yeah.
Right?
Okay.
So yeah, it's kind of annoying.
Yeah. All right. All right. Okay.
Yeah, that's.
Thanks.
No, thanks to you for correcting me. And okay, but right, I think we are basically done um, with the Heisenberg group, both in qubit and odd cases. Just really one very easy thing that I didn't mention is that this while operators factorizes. Namely, if you have, well, I just write for qubits, but the same in the odd case. This is just the same as F2 plus F2. And then you, with this decomposition, you have that W of VZ Vx is just factorizing a tensor product. So W of VZ1, Vx1, tensor product, all the others. And these are single qubit operators. This is something that I didn't mention before. Okay, I forgot to say. Now we can quickly introduce the Clifford group, but this is really easy at this point. So now it's just we have on, let's say, on this side the odd case, and here we have p equals 2. Because now it's kind of the same, but we have to address the different structure of the center fixing automorphism group. In the odd case, we basically have that this mu that introduced before. This is a function on the affine symplectic group, so it's a function of G and V, and this is just basically mu of G W of V, because we had this relation here, right? So this is SP and the product with FP to N. And what is the Clifford group is just the image of this group. So we just say that the Clifford group in this case is mu of the affine symplectic group. Yeah, very easy. And this is a finite group, so that's why last time I said that usually one remove the global phases to make the group finite. And this is not the full unitary normalizer, of course, but yeah, because we are disregarding all these terms. In the even case is kind of more complicated because you don't have this relation. Well, and that's coming from the fact that you cannot choose alpha to be 0 every time. And so you just write some conditions to the Clifford group to obtain a Clifford group. First one, let's say, is I want to make things simple. The thing is, in the even case, you can actually just lift your center fixing automorphism group to a bigger group that is that would be the affine symplectic group for even case. But this is not what we are interested in. But we require some structure, and basically the Clifford group is of course finite, and is in the normalizer of the of the while operators. Now this is fancy notation, meaning that we just take the while operators for all elements of the Heisenberg group, or maybe it's more correct to say of the discrete phase space. And now you also impose another condition, that is that the Clifford group, the quotient of the Clifford group with its center is basically the affine symplectic group. And now the interesting thing is that when you have all these properties, then what you get is a structure that is kind of similar in the, as in the hot case, namely if you take the quotient of the Clifford group with with this group here. Now this is just the symplectic group again. And while this would be actually this is free in the odd case, while it's not for in the even case. But if you take these properties for the Clifford group, then you obtain again this structure. And of course, even in this case, it's finite, but we were asking for that. And now, in principle, I may list the generators, but I don't know, maybe later on if there is more time, but I want to go to stabilizer now. At least I want to introduce them. So we go to stabilizer states now.
Sorry. Can you maybe comment why you need so the odd case for the Cliffords you described, and so for example the Cliffords are defined as this image of those affine symplectic transformations.
Mm-hmm.
So is this the same in the p=2 case?
No, the problem is that in the p=2 case, you don't have this because these are the center fixing automorphism, right? Is what you get with your compatibility condition. I mean, you just have to look at this relation here. And when you look at this in the odd case, these two conditions basically split. Because on the left-handed side you would have the symplectic form, right? And then your group is nicely structured in the sense that it's a semi-direct product group. And in the odd case, for example, you may choose alpha to be always 0, something that you can do. But here in this case, since beta is not antisymmetric, you cannot make this basically you cannot split the two terms, and in principle we would write alpha of G, because even alpha depends on the symplectic matrix. So this relation here is the origin of the differences between the two cases, and that's why you cannot introduce the Clifford group in the qubit case as easy as in the other case.
So can you say again, how do you introduce the Clifford group? So it should be the normalizer and it should be a finite. But
it's you just the idea is you take a finite normalizer of the while operators, And the idea is basically you want this. So yeah, you can also, if you want, forget about this condition. And yeah, the idea is that you introduce this group in such a way that you have these finite relations. So it's like you have the Clifford group is basically symplectic matrices and while operators. But yeah, it's kind of it's just technical, more technical.
So I know that in the end we need to end up with Hadamard's and CNOTs and stuff, right?
Yeah.
So to
Yeah.
end up there, I need to take a finite normalizer of while operators and choose them in such a way that the quotient with the while operators gives me the symplectic matrices.
Yeah.
And that will be the standard thing that we know, yeah? That's
Yeah,
the
exactly.
idea.
Yeah. Yeah. Yeah, this is all everything to obtain what you usually know as
Yeah,
the
but
Clifford group.
that's not very easy.
No, absolutely, yeah.
Yeah, but do you know if there's like a direct, straightforward proof that the regular minimal set of Cliffords is really the full maximal normalizer of Pauli's?
Um,
So,
no,
so this is nice because this will kind of tell me that I didn't miss anything, right? Because maybe there could be a CNOT prime or something, right? So
yeah, that's true, but I don't know any easy proof for that.
yeah,
So,
because I was asking myself, and this monstrous thing that you wrote down is the first time I kind of see something that looks like a complete characterization. Okay.
yeah, but that's the point, because when you write things in this way, anyway, you have all the Cliffords that you are interested in.
Yeah.
Up to the usual degree of freedom that we just forget about. This is with this picture on this side, you get everything anyway.
Yeah. All right. Okay.
Yeah, thanks. And okay, just to introduce stabilizers. Okay. Now the problem here again is that in the even case things are a mess, but things works nice in that case. Now we start with F2 to 2n, and now we take a subspace M, which is isotropic. What does it mean? Is that M is contained in its symplectic complement. This is something that we introduced last time, and this M is just the set of vectors V in F2. Sorry, in FP. Let's make things general, such that the symplectic form vanishes for any W. Now, let's say that P is not 2. Now we basically have that M times 0 is a subgroup of the Heisenberg group. And yeah, this is straightforward because you just remember the composition rule. We had basically, well, the first side is always abelian, but in the second side, when you write things, you have this factor here, right? This is VTWS. But if you are on an isotropic subspace, this is 0, and you have an abelian subgroup of the Heisenberg group. Now for P that is equals 2, this is not true anymore, because beta, is like we have beta instead of this nice symplectic form in the in the phase factor, let's say. But there are a couple of things that we can do in that case, and basically the idea is beta is vanish modulo 2 on M. Why? Because when you take beta mod 2, this is the symplective 4, right? And so that means that in this case, we can just write beta as 2 another function beta bar, which is defined on F2, right? Now you introduce another function that is completely arbitrary, but must satisfy one condition, namely this beta bar is such that we call this function delta, let's say. I hope I will not forget that. But this delta is from M to F2. And then this beta bar is equals to delta of V plus W minus delta of V minus delta of W. And you also have the condition that delta of 0 is equals to 0. Now, you have that the set M alpha that is defined as set of couples P to delta of V with V in M. Well, times 0, but basically this is a subgroup of the Heisenberg group in the even case too. And is abelian. Why it is the case? Yeah, it's just take 2 elements of this form and recall this relation here, and yeah, things works nicely then. I'm just speeding up now because I want to really define the stabilizer.
Why do you label it with alpha?
Sorry?
Why do you label M with alpha?
Because I'm changing notation on runtime.
Yeah,
I
okay.
forget about it.
I'm happy.
Yeah, but now what's the what we have to consider now is the while operator. So we previously considered this operator, and now we consider the restriction of this representation to M alpha. One note again. If P is not even, you can just choose delta equals to 0, and you go back to the first case, to this case, of course. So it's just the easier case for odd characteristic. Now we can consider this representation, but now this one is reducible because M alpha is abelian, and the thing is, yeah, by Schur's lemma, one knows that the only reps of an abelian group are one-dimensional. And in particular, this representation decomposes into character of M alpha. Let's call this character xi. This one. And now what's happening now is how is this decomposition? Now I'm kind of sketchy, but I hope that the idea goes through. The idea is you have a direct sum over basically all characters. And then you have this psi, and sorry, not so really
We lost the voice. And can you say like representation of what again, just for completeness?
sorry?
So like this W restricted to M delta? You
Yeah,
said?
I'm starting from this point again. The idea here is you start from your Y representation, but when now we restrict this representation to this M delta, which is by construction an abelian subgroup of the Heisenberg group. And since this is this is a representation of M delta and is reducible by Schur's lemma, basically. And it decompose, then you can decompose this representation into E-reps. And these E-reps are all one-dimensional since the group is abelian. So if you want to sketch this decomposition in something like this, you take characters of M delta, which are of this form. And yeah, you have the sum over all characters, and
we still see only the decomposition into psi characters.
yeah, and
That
then
was
here you have some multiplicity of these characters.
okay.
Yeah. Now the thing is, you in group theory there is this thing that is called the isotypic component, and basically is the direct sum of all the all the E-reps that appears with a given multiplicity. So give me a second, I'm mixing up things. Yeah, the idea is like you have this is just the vector space of this chi, but this is something like the direct sum of all the basically spaces V chi, let's say, where this V chi is the carrier space of psi, and this is the isotypic component, and then you can take the projector onto this component, and now this projector has some canonical form, let's say, and this is so we have this we fix this M delta, and then we have psi, and you can prove that this projector is of this form. You have a normalization factor given by the order of the group, and now we take the sum over all elements in the group, and then you take psi v bar. Now there is the prefactor given by this general thing in the for the even case, and then there is the representation. Now this can be proved, and for example, one reference is the book from Fulton and Harris, and usually goes under the name of, I think it's the second projection formula or something like this. Yeah, now here, for example, this function here, delta, must be chosen in a suitable way because you may be able to absorb the character into this function. So it's like this projection is not uniquely defined, but yeah, this is just the usual complication for qubits.
And you say you sum over m or m delta, because I think we had m as well.
Now, by definition of m delta is like you have to sum over this entry here because the function delta is fixed. So it's like, yeah, I can write sum over m delta,
yeah,
but it's
in m. Okay, yeah.
But now it's like you have this formula for the projection, and now if you take the trace of this projection, you obtain the dimension of the vector space, right? On which you are projecting. So let's call this isotropic component as G of m delta xi, and its dimension is just the trace of P. And now it's useful to remember that while operators are all traceless except for the identity. So this is just the trace of the identity over M. And then this is just P to the n minus the dimension of M. Okay, and now I stop because we are over time again. If M is Lagrangian, then you basically obtain that this space here is one-dimensional. So this here is 1D. And yeah, so it's spanned by only one state, and you call this state the stabilizer state. That's how you arrive to define stabilizers for any discrete phase space. And in this, when this M is not Lagrangian but is only an isotropic subspace, what you are getting at this point is just a stabilizer code, basically. But I think at this point we will start from here next time, and I'll talk a little bit more about these states.
Okay, thanks a lot. So we finished with the projector. We had the phase spaces before. Maybe somebody has some questions. Otherwise, I will just switch off. If somebody wants some questions for the others to see, if somebody watches it later. All right. I think. Okay. So thanks, Mirko, a lot so far. Okay.